As you keep progressing through school science lessons, you might notice that the focus points keep shrinking in size. From categorizing animals to learning about what makes up a cell, in some sciences it's easy to spot. From matter and chemicals to particles and elements to atomic structures containing of electrons, protons, and neutrons. But it keeps going. We've gone deeper, and it's time for you to join us. You might be accustomed to hearing that atoms are the smallest units of matter, composed by protons, neutrons, and electrons. However, this isn't true. Even these are made up of other things, subatomic particles. This is the standard model of elementary particle. Basically, the particle physics version of what the periodic table is to different atoms. There's a few different groups within. Each one represents a different and unique property. There are two branches within the elementary particles, fermions and bosons. Fermions are the building blocks of all matter and include quarks and leptons. Meanwhile, bosons are force-mediating particles that create the interactions between said fermions. Quarks are the fundamental particles that combine to form particles like protons and neutrons. There are 6 types, or flavors as we call them, of quarks: up, down, strange, charm, top, bottom. Each quark has a different mass, charge, and spin. These quarks can either form groups of 2 or 3, depending on the necessary charge of the final particle. For example, a proton with a charge +1 is made up of 2 up quarks and 1 down quark. A configuration of UUD with the correct charge, 2/3 plus 2/3 minus 1/3 is equal to 3/3, +1. Meanwhile, neutrons are made up of 2 down quarks and 1 up quark, UDD. 2/3 minus 1/3 minus 1/3 resulting in a charge of 0, which is neutral. Different combinations of quarks have different names. A group of 3 quarks is called a baryon. Pairs exist in a combination of quarks and antiquarks and are called mesons. Hold on a second. What are those? In most areas of physics, there is symmetry. For every particle, there is an antiparticle. They share the same mass but carry a different charge. An example of this is the electron and the anti-electron, the positron. The same way that we have up, down, strange, charm, top, bottom, we have anti-up, anti-down, anti-strange, anti-charm, anti-top, and anti-bottom. Leptons are a different group of fundamental particles, which aren't composed of quarks. They include electrons, muons, taus, and neutrinos. They do not combine with other particles to form a larger or composite particle. Electrons are negatively charged particles that orbit the nucleus of an atom. Muons are similar to electrons, but around 207 times heavier. They are unstable and decay very quickly, with a lifetime of around 2.2 microseconds, into an electron and 2 neutrinos. Muons are interesting, as although having such an extremely short lifetime, they are detected in a high quantity on the Earth's surface, even after long travels at nearly the speed of light. This is known as the muon paradox. The tau particle is similar to the electron and muon, but heavier. It has a negative electric charge, and it is the heaviest lepton, and the singular one that decays into hadrons or leptons, electrons or muons. Due to its very short lifetime, it is very difficult to measure. However, it provides us with information of quarks at low energies and the strong force. It was first discovered in the 1970s at the Stanford Linear Accelerator Center. There are 3 flavors of neutrinos: electron neutrino, muon neutrino, and tau neutrino, between which it oscillates. This oscillation occurs due to their mass and flavor eigenstates mixed. When created, they exist in a specific eigenstate, a characteristic determined flavor, but during travel, it consists of a combination. Each of these mass eigenstates travel at slightly different speeds due to the slight differences in masses, resulting in the combination changing and therefore the flavor alternating. They primarily interact through a weak nuclear force and gravity. They are abundant within the universe and can pass through matter, including us. They are the lightest known particle of mass. And as any other particles, these leptons have their corresponding antiparticles. Then there are bosons. Bosons are force-mediating particles, which are the interactions between matter. There are four fundamental forces in nature, and each one has its own unique boson. The electromagnetic force is mediated by the photon. This is the force that influences charged particles such as electrons and spans all effects from light to electricity. When two electrons repel each other, there is an exchange of photons at play. Photons have neither mass nor charge, but they carry energy and are the particle of light, traveling at the famous speed of light c. Photons demonstrate both wave-like and particle-like properties, a quality known as wave-particle duality. The properties of light are determined by the frequency and wavelength of a photon, while also operating with energy packets in the same way particles do. These particles can be detected in photon detectors within facilities such as CERN, specifically their ATLAS and CMS detectors, which use electromagnetic calorimeters, which measure the energy of electrons and photons. When they interact with the detector materials, particles are released, and the deposited energy is then measured. The strong nuclear force is facilitated by the gluon. It primarily holds the nucleus of an atom together and is the strongest of the four fundamental forces. Quarks are held together by this force to create mesons and hadrons. Quarks have a property known as the color charge, which can only be red, green, or blue. In this case, color does not refer to the visual color of these charges, but a quantum property. Gluons can also carry this charge, allowing further interactions. There are 8 types of color charges in gluons overall, each consisting with a color and an anticolor charge. Gluons were first discovered in the Petra accelerator in Germany in 1979. The weak nuclear force is mediated by the W and Z bosons. This force is seen in the radioactive decay and nuclear fusion within stars. W has an electric charge, positive or minus, and the Z boson is neutral. These particles are larger than some of the other bosons. The larger a particle is, the more quickly it decays, which means that this force is quite weak and only influences a smaller area. W bosons will usually decay into an electron and electron neutrino, or a muon and muon neutrino. Z bosons will decay into a variety of particles such as neutrinos, electrons, muons, and quarks. They were first discovered in 1983 at CERN. Finally, there is the gravitational force, the graviton. Although theoretical, its existence is necessary to explain the force of gravity. They are thought to be massless. The theoretical existence is supported by the detection of gravitational waves. If detected, the graviton would be vital to the development of a unifying theory. It is also thought to be emitted alongside other particles by certain astronomical objects, creating the gravitational fields we know and hear of, that we experience on Earth. Unlike the other bosons, the Higgs boson isn't a force carrier. Rather, it gives an attribute to other fundamental particles: mass. All bosons create a field, and the Higgs field is everywhere within space. The presence of a Higgs boson then excites this field, distorting it depending on the accumulation of mass within different spaces. The more mass, the greater the interaction. Sometimes this particle is called the God particle, after the book by Nobel laureate physicist Leon Lederman. Initially, it was meant to be called the goddamn particle, due to the contrast between it essentially being everywhere, but being very difficult to detect. It was discovered at the LHC at CERN by a group including a Peter Higgs. The standard model doesn't account for some things, such as dark matter and dark energy. However, it does provide a comprehensive account for the subatomic particles as we know, love, and experience them. Thank you so much for watching. Drop any topic recommendations in the form below and questions in the comments. I hope you've enjoyed enough to like and subscribe. Stay tuned for the next video. Have a wonderful day.